I love Google Sheets. They are easy to use, free, and powerful. I am also heavily involved in machine learning and teaching it. This is the second video from a series where I try to explain how neural networks work by re-implementing them in Google Sheets. In the first video, we've seen how a simple linear regression works, going from data generation to model implementation to optimization via gradient descent, and finishing off with a visualization of the error. Today, we're going to expand that implementation a bit by having several output units. Let's start with what we had last time. We will generate some data here. So two features, x1 and x2, and these would be random values, and generate a bunch of data for each. We would like to predict a function based on these two features, x1 and x2. And let's say that this function is just an array formula between x1 plus x2 plus a bias, which let's say that this is the cell for the bias. And the bias would be 0.5. I don't know. So what we want at this stage is to replicate the linear regression from last time, but implement it by multiple units. So let's redo the computation that we had for a single unit, and then we will duplicate those computations for the other units. Let's say that this is unit 1. For unit 1, we need to have some weights. So we have one weight for x1, one weight for x2, and one for a bias. And we will start by them being assigned some random values. As you probably remember from last time, we need W1, W2, and B to be updated by the stochastic gradient descent rule, which implied that we need to have the learning rate. Let's put some value here, placeholder. So if you remember, the recurring formula was J6, meaning itself, minus the learning rate multiplied by some value, which was the gradient. And we're going to put the gradient here. But if you do this, the initialization will always be 0. So we want to have a way to initialize W1, W2, and B with random values. At the same time, keep the update formula. So for doing this, we will use an if statement. We will say that if some condition is true, then use the random initialization here. And if not, use the update formula. Let's say this cell is equal to some magic word, which is init. So if J2 is init, then we're going to have the random initialization, and if not, we will have the update rule. Let's call this cell mode, and let's say that this is init. So let's replicate this for B and W. Let's make sure the references are correct. So the reference for the learning rate should be constant, and the mode cell should be also constant. So now, depending on the value of this cell, we either have a random initialization or an update rule. Now, regarding the gradient for W1, if you remember from last time, that was -2 multiplied with the average over the partial derivative of the loss function with respect to W1. And this is why true, all the correct values, minus the prediction. And the prediction is, let's compute the predictions here, this W1 multiplied by x1 plus W2 multiplied by x2 plus b, and multiplied by the x1. And we should replicate this for W2. So -2 multiplied by the average of the error, the correct answers minus the predictions, which again were W1 multiplied by X1 plus W2 multiplied by X2 plus B multiplied by X2 this time because it's a partial derivative of W2. And for B is again minus 2 times the average of the correct answer minus the prediction. And we don't have any parameter here. So this is a single unit. Maybe we can also add a loss function. So let's implement here the mean squared error. This is an average of the correct answers minus the predictions being W1 multiplied by X1 all raised to the power of 2. That's the loss function. Now that we have everything in place, let's delete this and see how the optimization is going. And it doesn't work. It seems that there's a bug. So I'm going to wait for this to finish and then investigate a bit. So there's two problems actually. One, it's fairly obvious. The loss is negative, and it shouldn't be negative because the mean squared error is an average over positive numbers. So it's clear that somehow this formula is wrong. And the thing which is wrong is that we've squared the prediction, but not the difference between the correct answer and the prediction. So this power of 2 should be outside, and that's one fix. Then there's the gradient formula. We've said that the gradient is the difference between the correct answer and the prediction. So the error term basically multiplied with the x1. And what we actually wrote is the multiplication between x1 and only the prediction and not the difference between them. So we have to add a couple of parentheses here. And this error is replicated for all weights. Let's try again and see how this goes. And now the optimization is moving in the right direction. We should expect to see W1 being close to 1, W2 close to 1, and B close to 0.5 because that's the formula for the correct prediction. And it slowly converges to that. Now we have one unit. Up until now, we just replicated what we did last time. Let's also add the error just to have a graph and see how things progress here. We're going to copy this part, which represents the error. And we're going to say array formula for this, the unit 1 error. And now that we have some error, let's make a chart out of this. And isolate unit 1. Let's add more units now. Unit 2. Let's switch to initialization just to not have any updates flashing. We need to have a gradient, a loss function, and the loss function is the average of the difference between the true labels minus the predictions. We should be writing an average over the array formula actually. raised to the power of 2. So let's copy this again. And this would be the initialization or the random or the current J11 minus the learning rate minus J12, which is the gradient. And let's push these to autofill and check them. Okay, and let's copy the gradients as well. Okay, minus the predictions multiplied. We only need to change the weights, which because we have new weights here for this unit. We're going to also add the error. And the chart. And let's also add another unit just to have 3 units. Okay, so fingers crossed, and let's see if it works. So it's working for the first and the second unit, and we're going to have to figure out why for unit 3 it doesn't work. So looking over, I can notice that the formula is wrong. So the circular update is based on the loss function, which is wrong. It should be based on the gradient cell. So this is J16, and this goes for every other cell. Okay, let's give it another try. And it seems to be optimizing, and it seems to be working. So uh, all the weights for all the units should converge roughly the same value, 1, 1, and 0, 5. The optimization finished, and we have roughly the same answer for every unit. Now, the interesting thing to note is that because we have random initialization and different random initialization for each unit, unit 1, 2, 3, optimization progresses at different speeds for unit 1, 2, 3, and one of them would finish earlier while another unit would be far slower. And this is just an example of why the initialization matters and why initialization will be a powerful element in learning because it will lead to somehow different outcomes. So this idea of having multiple units, even though in this situation, which is a toy example, will converge to the same values, because we have multiple units and because they have their own random initialization, we are able to start from different points in the optimization process and end up at different solutions. So everyone, this is it. We now have a clear implementation of linear regression in Google Sheets that has multiple output units. I really hope you've enjoyed this video. If you want to see more videos like this, you can go to course-ml.com and subscribe to my channel. You can also join one of our online machine learning classes, which we host regularly, or you can reach us out at ZNAI if you are a business in search of ML solutions. See you next time.